Hi, my name is Eugene Bagdasarian, and together with my hosts at Google, Peter, Stefan, Adria, Kaylee, and Marco, and my advisor Deborah, we're going to talk about Federated Analytics, our system for location heat maps under distributed differential privacy and secure aggregation. Aggregated location data benefits a variety of different services, ranging from public health applications such as monitoring the disease spread to traffic jams and so on. However, releasing this data requires certain privacy protections applied, such that public won't be able to figure out individual user locations and reverse engineer them up. The data should be anonymized and the locations mixed with others, and also certain differential privacy guarantees applied to the resulting set. However, applying and modifying the map and applying these privacy techniques would require a trusted server, where the server knows the locations of the user but performs these privacy modifications before releasing it to public. Another way to not share the sensitive information with the server is to use local differential privacy. For example, if the user wants to report where they are located in one of the 4 regions, they might contribute their own data but then add significant amount of noise such that server will not be able to figure out where the user was. And unsurprisingly, this results in a highly noisy maps that might not be very accurate or useful for the services. Instead, we propose to use distributed differential privacy, where we rely on a technique called secure aggregation that uses multi-party computation to securely compute a sum of user contributions and only present this sum to the server. In this case, users still add noise to their data, but significantly smaller amount of noise. However, the sum of the noise will present central differential privacy guarantee available to the server, and then later that can be released to the public. If we look in more details, we can rely on hierarchical histogram algorithm that looks at the map, and this is the map from a New York Times article of Manhattan and location data. So at the first time, users select from 4 regions only. So we built a quad tree with only 4 nodes, and users need to encode their location in to figure out where exactly they are located, and report. So user 1 reports they're in 1 region, add noise. User 2 also reports, and user 3 also report. Then once the map is summed up, the noise is enough to provide central differential privacy, and only this sum will be visible to the server. So if we look at the root node, we can count the numbers of points in each region and then make the decision whether we want to split the node and continue further. Such that if we receive those contributions, we, for example, decide to split all the nodes and split it again. And then for the second query, we again collect all the points, maybe different from the different people, but also applying a significant amount of noise. And then we make the decision again, and we collect the location data again, and then we make the decision again, and so on, until we end up with relatively accurate representation of Manhattan and with a high quality grid. There are a few challenges that exist in this algorithm that we address in our work. First one is how to select a threshold on deciding when should we expand or collapse the node. In expanding, we pick an adaptive threshold. The main motivation why we can adapt the threshold is that the server selects and knows the amount of noise that will be added, right? Because differential privacy budget specifies the exact epsilon. We can compute standard noise deviation, and can just set for the specific noise the threshold to be above 2 standard deviations of this noise. In this case, if we obtain a value above this noise, above this threshold, it will mean that we have for sure some people located in this region. Another challenge is, once even we know this threshold, we need to figure out how much privacy budget we spent across the subqueries. We could spend equal amount of budget. For example, if we have a budget of 1, we can spend 0.1 for 10 subqueries. However, we have you can observe that in first regions, in first subquery, there were only 4 regions. In 4 regions, essentially have higher user per cell count, and it would result, even if we had a lot of noise, it will still allow us to distinguish the signal from noise. Therefore, we can raise the amount of noise and therefore decrease the privacy budget and increase the threshold. On the other side, once we obtain a more fine-grained grid, a lot of noise might not be very beneficial, because we will essentially noise out all the contributions. So we would want to decrease the noise, so we increase the budget and decrease the threshold. So then we can get the most accurate numbers. And lastly, since we run subqueries multiple times, there might be different users participating. It might be different time frames, and we track all the regions across all the subqueries. So we always query the whole map, and because the user always can report where they are, whether on the more fine-grained or coarse-grained regions, and then we can adaptively decide whether we want to collapse certain nodes or expand those nodes. So then we can have more up-to-date map every time. All right, so here's an example how we use our algorithm. Assuming at a certain subquery k, we spent epsilon budget of 0.1 and obtained this map. We then analyze the amount of noise added and can decide on the collapsing and splitting threshold. And we see that, for example, top left corner has values below 10, and we can collapse those regions, and bottom right corner has 137, and we can expand the region. Then we run a new query with a privacy budget significantly higher than the previous one, and we obtain new values. And you see that these values might be different from the original values, and mostly because there is less noise added, or the distribution slightly changed between the queries, but it presents more accurate picture because there is the privacy budget is higher. All right, to demonstrate you the full algorithm run, so we use the same map with 100,000 users and a total budget of 1. And here you see that we start with just only 4 regions, and we spend a fraction of the privacy budget, 0.036, and the split threshold was around 2500, which is a pretty big. We still are able to split all the regions in the map, and then we continue slightly increasing the budget and decreasing the threshold, and then we continue more and more, and finally we spend 0.7 budget and get a very accurate map of Manhattan. All right, and to compare our results with some baselines, so we measure mean square error between original map and the map that we obtained, and we measure the total communication cost per user. We first start with the non-private baseline. In the non-private baseline, you essentially can submit 2 coordinates, x and y, which is means that the communication cost is 2, and mean square error is around 6.5, which is the result of the sampling error, since we only have 100,000 users, and the map we adapt from the image as having around 50 million. So we simply count luminosity as a user on the map. We also compare it to a couple of more baselines. So we first start with the flat baseline. In this case, we split the map in very fine-grained regions around 1024 to 1024, which significantly increases the communication cost. And since the map is very fine-grained, lots of noise is applied, so we get really not accurate result. We can similarly use count mean sketches to reduce the amount of communication. It slightly improves the performance. We also compare it to some couple of other works using adaptive grid decomposition and spatial decomposition, and both cases improve the results. And hierarchical histogram is the naive implementation without adaptive threshold and scheduling. In our case, we're able to significantly reduce the amount of communication and achieve very close to non-private baseline error. We also experimented with our algorithm on other data sets. We used humanitarian exchange data set and built these maps for Mayotte and Lagos, Nigeria. And you can see they also relatively accurately represent the underlying distributions. Finally, we wanted to sum up our contributions, so we designed a scalable and distributed differentially private approach that uses secure aggregation. In our experiments, we designed this adaptive algorithm, can adapt for unknown and dynamic distributions. It also works with dropout. Both provide secure aggregation guarantees and differential privacy guarantees. And we designed this adaptive mechanism for privacy budget schedule and dynamic threshold, and experimented on public geospatial data. Thank you so much.